In this video, I'll be talking about pacemaker action potential. A brief introduction of this is on page 287, first date, 2012. Okay, so let's get started. So before we talk about pacemaker action potential, one thing that we have to understand is what are the different ions that our pacemaker or our heart deals with. So let's not think about pacemaker, let's think about what ions is responsible for making any kind of changes in our heart. Well, one would be definitely sodium, and we're going to talk about that. The next would be calcium, okay, and potassium. So these are the three ions which is responsible for making some sort of effect on our heart. Now, in terms of membrane permeability, sodium membrane permeability is achieved at about 50 to 60 millivolts. Okay, so this is a positive number. So if sodium is there and sodium is across the membrane, that it would want to reach this number, this positive number, for it to be in equilibrium. So let's say this is our membrane and sodium is here and sodium is here. This is the inside of the cell, this is the outside of the cell. So the membrane potential would be around 50 to 60 or around this range if, let's say, both sides has 50. Okay, so this is positive 50. So around a positive 50 or 60 or around that number, that is the equilibrium potential of sodium. It's something that we can't logically come up with. This is something we have to remember. This is the positive action membrane potential of sodium. Every ion has its own membrane potential and it's different for every ion. For calcium, it's about 130 millivolts. Again, it's also going to be a positive number, and see how this is also a positive number, but it's so much higher than the sodium. But what about potassium? For potassium, the membrane potential is about negative 90 millivolts. Okay, so for potassium, so I'm just going to skip calcium, so the idea is the same. I'm just going to go to potassium. So for potassium to reach equilibrium, the membrane potential has to be negative 90. Okay, that's when it is going to reach equilibrium. So this is very important to understand in the concept behind pacemaker action potential. So now let's talk about why these positive numbers or these negative numbers makes any difference in our understanding. So the one thing that we know is that whenever we have a positive change in our membrane potential, the membrane potential is more likely to get depolarized. So increased sodium with a positive number or calcium, so increasing permeability of sodium or calcium tends to make the membrane potential more positive and more depolarized. And increased potassium, it would make the membrane more negative, hence repolarized. So now that we understand the different ions are responsible for making changes and how they're going to be making a change, now let's talk specifically about pacemaker action potential. So here I have two pictures of action potential of two different types of cells. On the left side we have a typical nerve cell, and on the right side we have pacemaker cells. They are a little different in terms of how they achieve an action potential. You see that whenever we have an impulse coming at a typical nerve cell, this is going to, reach threshold, and we're going to get an action potential. Okay, and this is, it's like you hit something with a hammer, and you hit it hard enough, only then it's going to go through. It's going to go through the object you're hitting it through onto the other side. So you have to hit the nerve cell with a certain amount of electricity or electrical impulse for the action potential to be generated. Let's say the number is, let's say, 10. I'm just making a number here. I don't know the real number. So if you hit a nerve cell with 9 millivolts, are you going to have an action potential? No. If you hit the nerve cell with 9.5 millivolts, are you going to have an action potential? No, it's got to be 10. It's got to reach that threshold number for the action potential to be generated in a typical nerve cell. Now let's see how it's different from pacemaker cells. With pacemaker cells, see how I drew this a linear line here? This is not a linear line here. This is a slope. And the reason for that is because in pacemaker cells, they have a slow depolarizing effect to generate an action potential. So, the cell is going to get depolarized, 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 and once it hits this number, it's ready to generate an action potential because this is a threshold. Once this threshold is reached, only then an action potential is going to be generated, which is kind of different for the nerve cell because in a nerve cell, there is a steady resting membrane potential, and once you hit threshold, only then it's going to generate an action potential. It's not like it's going to get depolarized slowly. No, you have to hit the nerve cell with a certain amount of voltage for it to generate an action potential. But in pacemaker cells, the cells slowly depolarize at a very steady rate, and then it reaches threshold, and then we have this action potential. So this brings to our next topic is that, so we know that a certain amount of voltage needs to be reached for it to generate an action potential in the pacemaker cells. And this action potential is due to a positive number, okay? It's due to a positive number. So what we want to do is we want for an action potential to be generated inside a pacemaker cell, we want more positive numbers entering the cell and less negative numbers entering the cell. So we want more positive ions entering and less negative ions entering. Only then the cell is going to be in a positive state, which is the depolarized state. So again, let me explain that in terms of illustration. So let's say this is our membrane, this is the outside, this is the inside, and we want our pacemaker cell to be depolarized. So we want to encourage more sodium or more calcium to come in because these are more positive. And we have potassium here. We know that there is a lot of potassium inside. Intracellularly, potassium is really high. But what we don't want is more potassium to come in. If this happens, what's going to happen? The cell is going to be repolarized, and the cell is not going to go into the general depolarization. So we want to put a stop to this incoming of potassium, and we want to encourage the incoming of more sodium and calcium into the cell.